Hi everybody, this is Mr. Folly, and welcome to podcast 8.8. We're going to talk about kinetics, changing concentration over time, reaction current steps, rate determining steps, and speed. So let's hop to it. Kinetics is how fast a reaction occurs. Explosions are fast. Mummies decompose slowly. Buildings erode slowly. Now, before we had this glorious 8 to 12 inches of snow by my house, it was springtime. Animals were out running everywhere. And there was a squirrel that got run over in my street, or runned over. And see, some people see dead animals and see sadness. I see an opportunity to put up my G.I. Joes and look like they've shot these things down. Now, this squirrel would have decomposed quickly if it was 90 degrees outside, but it wasn't 90 degrees outside. It's 20 degrees here in glorious Indiana. So if it's 20 degrees, the squirrel is preserved, and I will have that squirrel to play with much later when it melts out of the deep pack of snow. So how fast reaction occurs, this can be changed. Okay, back to that. Can be changed. And we'll talk about how. All right. So rate is measured in change in something per unit time. So rate is how fast you drive your car. Miles per hour, right? If we're trying to figure out how long it takes to do a test, you can do how many questions per minute or something like that. You can figure out your timing for the ACT or SAT or something like that. So this could be molarity per minute or milliliters per second or something like that. And we'll use both of these in labs that we're going to do. Have fun. Find the rate. So here's an example. So maltose concentration in micromolality. Whoops. And then time per minute. Stop doing that. All right. So if we want to find the rate, it's going to be the change in something. So it's the change in this over time. So the change in this is from 0 to 11.5. That is 11.5 over time. 60. Which would be, I wish I had my calculator, but I suppose my phone will do. Isn't that handy? 11.5 divided by 60 is 0.192 micromolal per, whoops, not minutes, not seconds, but minutes. Okay. And then there's another lab where time it takes for this cross to disappear. So the time it takes at these different temperatures, it's different for each one. Okay. Now this is a lab that we're going to do, and it's kind of tough to figure out because this has a one-time event. Okay. So if it has a one-time event, the way you can figure out the rate of something is that rate is the inverse of time. So the inverse of time means that rate is pretty much, I'm going to put my squiggly thing, time to the negative 1. All right? So if all I have is time, what I can talk about for rate would be 195 to negative 1. Okay? So this one isn't calculated quite the same way. This is what we're going to do all of the time, but every once in a while this happens. So we're going to do a lab where you're going to be looking at a cross and looking through a beaker. Oh, that's a terrible beaker. You're looking down. Here's my eye, or here's my person leaning over, looking down here. And what's going to happen is this is going to fog up, and eventually you won't see it. So that's the time it takes for the cross to disappear. Catalysts speed up a reaction but are not used up. We talk about this in biology. In biology, catalyst is called an enzyme, and that's a biological catalyst. If you cut a loaf of bread with a knife and nothing else, so I have a loaf of bread, and I'm an astronaut, of course I am, and I have a knife. I'm trying to cut a loaf of bread with a big knife. It's really hard if I don't have a table to cut it on. So if I have my other hands holding the bread, I'm doing it and seesawing it back and forth, and it's not happening. But if I had a table to cut my bread on, it's really easy. So a catalyst is like a table. The table's still there. The table doesn't change, but having it to slice my bread, chop, 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 nice and easy. Okay. So a catalyst would look, when I write it like this, these are the steps of a reaction. It's just step 1, step 2, step 3. AB yields AB. AB yields C plus B. Do you see how this was a reactant? and a product, so it reforms. Okay? So my catalyst is B, because it's a reactant and it reforms, and it will speed up the reaction. There's also, notice how AB forms. AB, please write this down, is an intermediate. An intermediate is something that forms, but is used up. So when I look at this overall, see I have A and B. Do you see my B's cancel? You see how my intermediate of AB cancels? You see how my intermediate of D cancels? So I would have A plus, see how these are still on the left-hand side, C plus H yields, whoa, it looks like nothing. Oh, not H. I'm sorry. That's what I get for not looking at my arrow very well. A plus C yields H. And that's it. Because those are the ones that are left over. See how this goes? Oopsie, sorry about that. Rate determining step is the slowest step. So if I'm making a million cakes, let's say there's a few steps to making a cake. Let's say you have to mix the batter. That takes 2 minutes. You have to bake the cake. That takes 20 minutes. You have to frost the cake. And that takes 5 minutes. Now if I have to make a million of them and I have one oven, okay? Or even if I have a bunch of ovens. So if I mix a whole bunch of batter and during the 20 minutes, can't I do that? And during the second cake, can't I frost? So wouldn't I always be waiting for the cake to bake, right? So if I have to make a million cakes, basically it takes a million times 20, right? Because 20 is my rate determining step. So what's up with the catalyst effect? So let me just give you an example here. So if this takes 20 million minutes, if I found a way to mix the batter shorter, that would save me maybe a minute. But if I found a way to cut my baking time in half, then 20 million minutes becomes 10 million minutes, and that is a huge time saving. So the catalyst would affect the rate determining step. Make sure you know that, boys and girls. Okay. Collision theory. In order for a reaction to be successful, particles must collide with enough energy and the right orientation. I had a creepy chemistry teacher who told me that this is like kissing. So if you're kissing, all right, here's some more wonderful drawings by me. If you're going to kiss somebody, so pretend you're that person in the hallway. And you're about ready to smooch you up here. In order to kiss, they have to collide. They need to touch with enough energy and the right orientation. So enough energy and the right orientation. And the right orientation. So enough energy you got to have it be a good kiss. You got to have the right energy. Too much, you're chipping teeth. Not enough, you don't even know they're there. And the right orientation. See how they have this nose issue? I was tortured with that, so I feel honest. But all reactions, every reaction, even decomposition reactions, must collide with enough energy and the right orientation, or it doesn't work. A better chemistry picture is if I'm trying to make two NOs and bromine, see how if they hit like this? Hey, it can work. See if it hits like this? I can still get all of those. If it hits like this, there's no way the bromines can hook together. And now this just shows reactions rotating 90-degree angles, and remember, there's much more than 90 degrees. Success rate is incredibly low, much like your chance of kissing. Imagine putting pen caps and pens in a box. Lid on it. I have a pen and a pen cap. Okay? And I put it in there, and I'm going to shake it until my pen cap gets in the pen cap and it snaps closed. That's not going to happen. Okay? It will take forever to do. In chemistry, 1 out of every 10 to the 12, that's almost never is possible. So how can I affect the rate of a reaction? Okay, so surface area, why? So if I increase surface area, I have more places for collisions. So more successful collisions are possible. Concentration. If I increase the concentration, that means there's going to be more particles in there. More particles means more collisions. And more collisions, so more successful collisions. Remember, successful collision equals more reactions. Rx plus G equals reaction. Temperature. So if things move faster, that means faster, equals more collisions. Oh, okay. Now, faster also means not that you have more collisions, but in addition to that, more collisions that occur are successful. That's energetic enough. Okay, so more collisions are energetic enough. So what that means is that when they collide, there'll be even more. That 1 to the, remember I said many of them are 10 to the 12th? That 10 to the 12th might drop to 10 to the 6th. That's a million times better. Woo! Nature of reactants, simple equals easy reaction. Okay? So if I want to build a house, it's easier to build a house out of bricks than it is out of pentagons. That's not a pentagon, but you can do. And a catalyst speeds up a reaction. New mechanism, move faster. So review. Kinetics, look at rate. Reaction occurs in steps, and the slowest step determines the rate. So remember, that's the rate determining step. What is it? Intermediates are formed and then used up. Catalysts are reactants and products. Collision theory, bang up job. Get it, bang up job. So funny. Kill me. Doodles.